All right, we're starting. Standards are going to be held high. Standards are going to be held high in our
But they have so much weird stuff like
Really? Oh, I saw you when I was doing like the move. I was watching.
I know. No, Carmen actually said you did really good. She said you did better than more studies when she was here.
Okay, so we're going to continue with max and min values. Not much to do here. I just want to do, well, one example, and in the next, for the other examples, we're actually going to cover them in curve sketching, so we'll just move on after this one. So we spoke about absolute max and min, right? These were the largest, smallest, respectively. Y values on some interval A, B, which may be endpoints. Right? We'll talk about this a little more as well when we get to optimization. We also talked about local maxes and mins. And these were the largest, smallest Y values in some small region. Right, so we discussed that this was talking really about local when you zoom in and you're in some small region. Right, so you can have like this guy, like that. Let's say that's our A and that's our B. Then this guy here would be the absolute max and min, absolute max. But these guys here would be local maxes. Right? But the difference is the Y value for this one is, well, it should be higher. The Y value for this one is the biggest on the entire interval, while in small regions, this one is the biggest. And that was kind of the difference. We also spoke about so to find absolute max and mins, the method we used was called the closed, well, we didn't actually use it, I'm going to use it now, closed interval method. To find local max and mins, we had two options. We had the first derivative test and the second derivative test. So now I want to do one example where we're using this guy, and examples where we're using this guy, we'll save that for curve sketching because we're actually going to have to locate local maximums and minimums to do curve sketching. So I'll do a simple example because they don't really get more difficult, really. Right? Usually the question that I'm requiring you to find an absolute max and min, it's going to be where I'm just going to literally give you a function, give you an interval, and say find the absolute max and min on this interval. So we're done. Did I do the one with x squared for you guys?
Yeah, we did that.
Yeah.
I think I did. x squared so 4 minus 4x squared just 3. I think we're actually going to also graph this guy. Yeah, so we're actually going to graph this in detail afterwards. So let's just remember, how did we do this? What did we have to check? What was the first thing we had to do? Find absolute max and min. This first step was what?
Find the intermediate.
You need the critical points. Right? So this was where your derivative is equal to 0 or undefined. So this would mean what's the derivative of this?
4x to the third minus 8x.
You know it's always defined, right? It's a polynomial, so that's not going to be affecting anything. How do we solve this equation? Huh?
You might factor in x, or like x times 4x squared minus 8.
Well, you can take out a 4x, and what would we be left with?
X squared minus 8. That's
So it's 2. I didn't want to split this so long. Because I wanted to illustrate something of this, I think. And so we get x is equal to 0, right, for this one. What do we get for those?
Also minus the square root.
Right, either radical 2 or x equals minus radical 2. Right, because this you can actually factor as a difference of squares, x plus radical 2, x minus radical 2. Well, we get these 3 points, right? So now what do we do? We want to evaluate the y values. Remember, the goal is to find the largest y value. Okay, so who do I evaluate? So first of all, you need to remember that when we're talking about absolute max and min and we're given an interval, the interval is going to be important. This is one of the things I want to emphasize here. So now, are all these numbers in the interval? Is something that you always have to check.
Square root of 2's out of it.
Right. Notice that this guy is not in the interval. So there are times when in the step 1, you can get a bunch of answers, but not all of them are to be considered. You're only considering the ones that are in the interval. And so here, there are 2 values that I would check, 0 because 0 is in this interval, and minus radical 2 because minus radical 2 is in the interval, because radical 2 is roughly 1.4. So here we're going to find y of 0. I can call it f of 0. Which is 0. I'm going to find y of minus radical 2. So I plug in minus radical 2 into here, and what do I get? Well, radical 2 squared is 2. That gives me 8. So radical 2 squared is 2, and then you square that again. That brings to the 4th power, so that gives you 4. And that's all. Then step 2, we check the endpoints. So it means I'm going to find y of to minus 2, and I'm going to find y of 1. So this is going to be minus 2 to the 4th minus 4 times minus 2 squared. And that gives us what? That's 16 minus 16. And also 1. And so that would be minus 3. So the last step is to compare. So what would be the answer now? Who would you describe as the absolute max and the absolute min?
Is -2 the absolute maximum?
Well, here, all the y values we want to consider are 0, minus 4, 0, minus 3.
So then
What's the largest y value? 0. So y of 0 equals, and this gives you the same value, so you write that as well, equals 0. Is your absolute max. That's the largest y value that this function attains on that interval. And absolute min is this one, which is -4. That's the smallest y value. So you write y of minus radical 2 equals minus 4. And so that would be the answer. So a little more to do here than the other one. One is to notice that when it comes to absolute max and min, the interval is important. And so there are times when you'll have answers in what you're doing, but not all of them should be considered. So in step 1 we got 3 answers, but only 2 of them were considered because only 2 of them fall in that interval. You can also have a situation where multiple things are giving you the same value, but you can just list all of them and say that's the absolute maximum. So we're going to move on to curve sketching. There's a step in the process of sketching a curve where you're going to have to find local maximums and minimums. Anyway, so we're going to do the examples for that there. So you can grab your handouts and we'll start that. And so now full disclosure, curve sketching is going to be one of the longest kind of problems you're going to be doing in the next test and in this course, in fact. So let's take a deep breath and we're going to get through it. It's also going to put together a lot of ideas that we've been building so far, right? So we're going to have to remember how to find limits. We're going to have to remember how to solve equations. We're going to have to remember how to find domains. We're going to have to remember how to find x and y intercepts, and then we're going to start using derivatives. So a lot of stuff is going to come down in this curve sketching topic. I probably only want to do 2 examples. We'll see how far we get through. But yeah, it's going to be very similar. So this is curve sketching handout. And these are the steps. So basically, we want to sketch a curve, want to figure out how a graph looks like, and we want to do it with more accuracy than we've ever done before in our lives by hand. So that's going to basically the idea. So these are the steps. Again, these are always the steps. Order doesn't matter as much here, but I would recommend that you always do it in this order. It sort of makes sense to do it in this order, and you want to practice doing it in a certain order, so that when you're in a test, you never forget about what you need to do next. You'll know what you need to do next. So knowing what the domain is going to be very important, and in the first example, we're going to see why. You need to remember how to find x and y intercepts. I briefly described that there. You're also going to need to find asymptotes, and I sort of define the two kinds of asymptotes that we care about. There are other kinds, but we'll only care about the horizontal and the vertical asymptotes. Maybe I'll mention something here. So when you're talking about horizontal asymptotes, this is talking about some horizontal line that the function approaches as you're going off to infinity. So you can have a graph, let's say there's this horizontal line here, going through 1, and as your function is going to infinity, it's leveling off, getting closer and closer to 1, probably never touching it. Right? This line y equals 1 would be considered a horizontal asymptote. Now you might have another line over here, say that's at -1, where your function does something like this. And it eventually levels off. Right? So in this case, your y equals 1 and y equals -1 are horizontal asymptotes. Okay, so that's the idea behind a horizontal asymptote. It's some horizontal line that your graph approaches as it goes to either positive infinity or negative infinity. It might not exist, but it's something that you have to check for. Right? Vertical asymptotes are a little bit different. I want you to notice here that I did cross this horizontal asymptote. It's possible to cross horizontal asymptotes. People don't tend not to realize that, but it is possible. The other kind of asymptote, though, vertical asymptotes, we never cross vertical. So that's the idea behind horizontal asymptotes. If you look at the vertical ones, this is basically some vertical line that your graph is approaching. Right, so let's say we have this here. And notice that I always draw them in broken lines going through 1. And you can have a graph doing something like this. On the other side, it might be something like this, kind of like a 1/x almost. So here, your graph is approaching this vertical line, but it's never actually touching it. So the idea, something that's important here, you can't touch vertical asymptotes. Right? You can cross horizontal ones, but you'll never cross vertical ones, because these are pretty much always going to be x values for which your function is undefined. So a very common way to find these is if you're given a fraction, figure out where the denominator is 0, and it might create a vertical asymptote. If the numerator is not 0 at the same time, so that you can factor and cancel, in that case you get a hole, and we looked at examples like that way back in the beginning of class. Right, so there was like when we had the x squared minus 4 or x minus 2, there was a hole at x equals 2. It wasn't a vertical asymptote. But that's because you could cancel something from the top. If you can't do that, it creates this thing this x value that you can't touch, and your graph just avoids it. And it does so in this sort of manner. So if you can find points where your graph shoots up to infinity or shoots down to negative infinity at a finite value, that will be a vertical asymptote. And as I said, usually this is going to show up in curve sketching where you have a fraction or rational function, and it happens when the denominator equals 0. But these are important concepts to understand. Okay. Once you do that, we're going to move on. Once you deal with these two kinds of asymptotes, you're going to move on to find intervals of increasing and decreasing and local maximums and minimums. So that's where we're going to do like the first derivative test or the second derivative test. And then we'll move on to so-called concavity, which again we described in that big table when remember that table I gave you guys where I spoke about f prime, f double prime, and I spoke about what they told you, how to figure it out, blah, blah, blah. That's coming back. That's what we're going to be doing as well. And then finally, we're going to use all that information to sketch the graph. So we're going to put together a lot of ideas. So take a deep breath and let's actually do it. Let's do the first example. You're going to see me go through the steps. We're going to indicate the steps when I'm doing it. But it's still going to be a lengthy process. So let's start by sketching a graph that we already actually know how to sketch by hand, but I want you guys to see in principle how we would go about doing it in detail, especially if we didn't know what it looked like before. So in the first step, as we discussed, we're going to find the domain. What is the domain here? Domain of the function.
All the numbers except 0.
Right. Anything except 0, it's a fraction. You can't divide by 0. All real x such that x not equals 0. Okay, so that's cool. Let's move on to the next one. Let's talk about our intercepts. Now, intercepts here refers to your x-intercepts and your y-intercepts. How do you find x-intercepts? Y equals 0, solve for x. So this means that 0 is equal to 1 over x squared. In this case, there is no solution. A fraction can only be 0 if the numerator is 0, and the numerator here is never 0. You can also realize that if I multiply both sides by x squared, I get 0 equals 1, which is obviously nonsense, so there is no solution to that equation. For the y-intercept in general, you set x equals 0 and solve for y. But x is not 0, right? Because we can't actually plug in x equals 0 into this function, so that also has no solution. So far what we know about this graph is that its domain does not include 0, and it actually has no intercepts. Right, so we're going to be building up a picture here. Right, so it never touches the x-axis, it never touches the y-axis. Third step, we're going to look for asymptotes. Let's start with the horizontal asymptote. Now remember, horizontal asymptotes refer to the behavior of the function as you're going off to infinity or negative infinity. Therefore, we take limits. So we find the limit as x approaches infinity of our function, and the limit as x approaches negative infinity of our function. What's that answer? 0. Bottom is the same thing, right? It's bottom heavy. It's a ratio of polynomials, the degree on the bottom is bigger. Things like that you're going to have to remember. We did all that already. So once you get a finite number, once you get a number, that's going to be your horizontal asymptote. If you get infinity or does not exist, there is no horizontal asymptote. You have to get a number. So clearly, as we move off to infinity or negative infinity, the y value of this function is getting closer and closer to 0. That's how we conceptualize limits. Now the vertical asymptote, you sort of have to figure out a point in the graph where it shoots up to infinity at some x value. And this pretty easily is going to be, you're going to set the denominator equal to 0. So this means x squared equals 0, which means x equals 0 is a vertical asymptote. Note this cannot be cancelled by the numerator. So if I had like some sort of, if I could factor out an x squared from the numerator and cancel the denominator, what it would create is a hole. It would not create a vertical asymptote. Right, so here I found somewhere the denominator is 0 and I can't simplify to get rid of that problem. And so we end up with a vertical asymptote. So far what I know about this graph is this domain does not include 0. It does not touch the x or the y-axis. As you move off to positive infinity or negative infinity, it approaches 0, and x equals 0 is a vertical asymptote. Let's continue. So in step 4, there are 4 things we're going to do in one shot. We're going to figure out where it's increasing, where it's decreasing, where it has maximums, where it has minimums. We can do all this in one shot because there's exactly one function that can give us all of this, the first derivative. So what we're going to do here is if our y is 1 over x squared, what we're going to do is we're going to find the derivative. What's the derivative of 1 over x squared? Over x squared, you look at it as x to the minus 2. Do the power rule. Minus 2 comes down, you get x to the minus 3, you have this step. And so what we're going to do here is the first derivative. So we're going to find the critical points. This means minus 2 over x cubed equals 0, or minus 2 over x cubed is undefined. This guy, again, no solution. This guy means x equals 0 is when that's undefined. So 0 is our only critical point. Now what we're going to do is the first derivative test, which I described last time. So in the derivative function, I'm going to plot a number line where I plot the critical points on this number line. I'm going to plug in numbers on either side of this critical point. It doesn't matter which points you pick, so I'll pick some easy numbers, plus or minus 1. As long as you're not interfering with some other critical points, once you're in between critical points, it doesn't matter what values you're going to pick, because the function will stay the same in terms of the sign of the slope. So what I'm going to do is I'm going to take each of these values and I'm going to plug into the derivative. So over here I'm going to look at minus 2 over minus 1 cubed. And what? Yes. But the important thing I want you to worry about here is really the signs. I don't really care about the value. So what I want you to notice, because when the function is more complicated, I don't expect you to be evaluating all these. That's wasting a lot of time. What I want you to notice from this fraction is that the numerator is negative because it's a negative 2. The denominator is the cube of a negative, so you have a negative divided by a negative, which makes it positive. The actual value at this point we don't care about. Similarly, if I plug in 1, this is minus 2 over 1 cubed. Notice the numerator is negative. The denominator is the cube of a positive number, therefore it's a positive. And that's negative divided by a positive, so that means overall it's a negative number. Now in the first derivative, what does it mean to be positive? Increasing. It means your graph is moving up as you go from left to right. And negative means the opposite, decreasing. The graph is moving down as you go up. What does that tell us about 0? No. Why not? 0 is not in our domain, so you have to be careful. This is why part 1 can come in handy. Don't just oh, it's coming up, then it's going down, that must be a max. Not necessarily. Depends on whether your function is defined at that point. 0 could be a max potentially, but we know it's not because it's actually not in your domain, right? So we spoke about the Fermat's theorem and what it means for maximums and minimums, and so that's why you have to really be careful. You can't, it's not automatic that if the derivative is 0 or 100, if it's a critical point, that it will be a max or a min. So you do have to make sure that your information is consistent everywhere. So this is nothing because it's not on the graph, it's an asymptote. So you have to be very careful how you're reading these graphs. So here what we can say is we will note all the information we found. Where is it increasing? On the interval from -infinity to 0. It's decreasing on the interval from 0 to infinity. As for maximums, there are none. As for local minimums, there are none. This brings us to step 5, where we're going to talk about concavity and inflection points. We can talk about both at the same time because the second derivative helps us with both of these. So we're going to find the second derivative, which is going to be this guy. I'm going to use the power rule on that. You're going to get 6x to the -4, which is 6 over x to the 4. Now, similar to the first derivative test, we're going to find the critical points here because we're going to figure out the signs. So this is where 6 over x to the 4th equals 0, or 6 over x to the 4th is undefined. This guy in solution. This guy is when x equals 0. So now what I'm going to do, so I'm going to again do a number line, but this time I'm doing it in the second derivative. Plot 0, pick random numbers, plug into the second derivative. So over here, I have 6 over -1 to the 4th. Over here, I have 6 over 1. Positive or negative? Positive. And this is also positive. Right. It's a positive number divided by something to a 4th power, so that's always going to be positive. What does positive mean here?
Increasing.
No. First derivative tells you about increasing. Concave up. Positive up and happy or smiling. That's talking about the shape of the graph. When you get to the second derivative, it does not tell you about increasing or decreasing. It tells you about concavity, shaped like a smiley face or a frowny face, essentially. So this tells you that we're concave up here, concave up here. Any inflections? Remember, an inflection point is where you switch concavities, which means the sign has to change. That does not happen, so there are no inflections. So I can talk about where I'm concave up, where I'm concave down, and where I have inflection points. I'm concave up from -infinity to 0, from 0 to 1. Concave down, nowhere. Inflection points, none. And this leads us to the last step, where we can actually put all this together. So at this point, you go through step by step, and you start to put all the information that you found on the chart. I'm going to show you how to do that. So first thing, intercepts. Were there any intercepts? No intercepts. Next thing, asymptotes. Were there any asymptotes? Y equals 0, which is the x-axis, was a horizontal asymptote. You draw those with a broken line. So y equals 0 is HA. X equals 0, which is the y-axis, was also an asymptote. In general, you want to draw the broken lines faintly, but if they're on the axis, you have to be a little darker. So x equals 0 is EA. Next thing, we moved on to increasing, decreasing, or maximums and minimums. Where were we increasing? We're increasing on this whole side, right? From -infinity to 0. So what I would do is I would draw a little chart here, a little arrow going back saying I'm increasing from here backwards. We found that we were decreasing on the other side, so we're decreasing here. We also found no maximums and minimums. So next we'll move on to concavity. We realized we were concave up from 0, from -infinity up to 0, we were concave up. And from 0 to infinity, we're also concave up. There were no inflection points. So this is all the information we have for this graph, right? Some graphs will have more information than others. So basically now, I know that the picture I'm going to draw, the graph is going to be increasing concave up, which means it's increasing and shaped like a smiley face. On this side, I can be drawing a graph that's decreasing concave up, decreasing and shaped like a smiley face. So now the question is, how do I start drawing that? Would that work? Why not? Yeah?
Because you go past an asymptote, you're an asymptote.
It's not that I go past an asymptote. Like a horizontal asymptote is okay to cross. But what would happen if the graph looks like that? I would create an x-intercept. I know there are no intercepts. So when you're drawing the picture, you have to make sure everything's consistent. You're always double checking everything you're doing. So there's no way the graph could look like that because I cross the x-axis. Which means if I'm increasing and I never cross the x-axis, I have to always be above the x-axis. So that's the graph. Similarly, if I'm decreasing and shaped like a smiley face, I can't do that because I would cross the x-axis and create an x-intercept. So I have to do this. And this is how we could draw 1/x. I mean, we knew that already, but it's nice to see that what we were doing is consistent. We'll draw a more complicated graph next time and move on to optimization. And so all the homeworks for not the curve sketching homework, but the homework right before that of absolute max and min, that's due tomorrow.
Read tomorrow.
Sorry.
You're really